So it's a great pleasure to introduce the next speaker in our panel session, Yeonwook Jung, who's going to tell us about thickness and its applications. Please.
Thank you so much. 6 months ago, I visited my advisor's office as a very inspired master's student to look for a potential research topic. He gave me several topics, but I had no idea which project to choose from. But on my way back home on a train, I was reading some of his suggested papers, and there was one keyword that kept attracting my attention, and it was about contour sets and thickness. And why am I telling you this story? It's because the purpose of this presentation is to share with you the questions and answers that I found while I was investigating these notions. So my name is Yeonwook Jung. As I was introduced, I'm a master's student at San Francisco State University. My advisor is Dr. Chan Lai, and I'm very grateful to have this opportunity to discuss about my results. So let's start with some background. Contour sets are well known to be important in analysis, topology, and fractal geometry. For example, we know the well-known example of the middle third contour set, which we start with the closed interval, we remove middle thirds continuously. And this is an example of more general definition that we're going to adopt, which we define contour set to be any compact, totally disconnected, and perfect subset form. Although we know many things about contour sets, some of the basic questions are still very difficult to fully answer. For example, it's about intersections of contour sets. We can ask ourselves, when do middle third contour sets intersect? For example, if I start with one middle third contour set, I translate another copy of it and ask if they would still intersect. And the answer is actually yes. This directly follows from the fact that when we add two middle third contour sets, we actually get a full interval from 0 to 2. But we can ask a broader question. Just like the middle third contour set, when would general contour sets intersect? And this question actually turns out to be quite difficult to fully answer. In order to make some progress, we're going to consider the notion of thickness. So thickness is a very useful notion that can measure the size of contour sets. For example, let's return to the well-known middle third contour set. Here we're going to denote the gaps G1, G2, G3 in decreasing order, and L1, R1 for the left and the right intervals that remain after we remove the gaps. Here we're going to compute the ratio of what remains over what we have removed. So for example, for G1, we're going to take the minimum of the length of L1, R1, and divide it with the length of the gap G1. In this case, we'll get 1 because it's middle third contour set, and all 4 different gaps too. So even if we take the infimum of all of those ratios, we'll still get 1, and we define that to be the thickness of this middle third contour set. In 1970, Newhouse defined an important notion called Newhouse thickness, which exactly defines this notion for all contour sets. And this is very useful because we can have the following result. If two contour sets are thick enough, so they have big enough sizes, meaning that the product of thickness is greater than or equal to 1, then those two contour sets are guaranteed to intersect. And this is precisely stated in the celebrated Newhouse gap lemma, which he also proved in 1970. So if we have two contour sets whose convex hull is not disjoint, and if one contour set does not trivially lie in the gap of the other, then is it enough to take the product of those two contour sets, product of the thickness of those two contour sets, to be greater than or equal to 1, which would directly imply that they would intersect. We can slightly generalize our example of middle third to middle epsilon, and we'll have a very intuitive thickness, which is 1 minus epsilon over 2 epsilon. So it would be very large for small epsilon and very small for if we remove a large epsilon. However, note that in order to use the Newhouse gap lemma, we need to guarantee their product of thickness to be greater or equal to 1. And this will never happen if one of the contour sets have thickness 0. So it would be very interesting to ask, when would contour sets with thickness 0 intersect with another contour set? To answer this question, we're going to introduce a lemma which we call containment lemma. So first, we fix the notation. We're going to call the intervals and the gaps using length n binary word consisted of 0 and 1. 0 for the left-hand side, 1 for the right-hand side. So for example, I0, I00, I01, and so on and so forth. And our containment lemma states the following. Suppose we have two contour sets, C and C tilde. One has to be contained in the other contour set in terms of convex hull. Then, if the one if the one with the larger convex hull has smaller gaps than the one that is contained in for each generation, then we can conclude that those two contour sets will intersect. How can we prove this lemma? We're going to prove the following statement using induction. The statement is the following. There exists two nested sequences of binary words, sigma for C and sigma prime for C tilde, such that the interval labeled by sigma n for C, interval labeled by sigma prime n for C tilde, will be contained indefinitely throughout all generations. So let's see how we can prove this. For the base case, this directly follows from our assumption that the convex hull is contained. We assume the induction hypothesis. Suppose for generation n we found such words. Now all we have to do is construct the next word where the containment will continue to happen. So we consider the following diagram, and here we recall our assumption that the gap of the one that's larger should be less than the gap of the smaller one. Because of this, b tilde minus a tilde should be less than b minus a, which in turn implies that a should be less than a tilde, or it has to be b tilde less than b. In this diagram, we've drawn the case where a is less than a tilde. And note that we have the next generation where one interval is contained, the interval of C is contained in C tilde. So by induction principle, this is gonna hold for all n. And now to conclude the proof, after we have this containment, we're gonna choose 2 points, one in C and one in C tilde, such that their length is gonna be less than the length of the interval of C. And because the length of interval of contour set C should go to 0 as n goes to infinity, because it's totally disconnected, the distance between 2 points that we chose will also approach 0. And C tilde are compact. Therefore, the limit point should exist in C as well as in C tilde, implying that C intersection C tilde is not empty. So we can use this to directly construct contour sets that we're looking for. For example, if a contour set C had thickness greater than 0, all we have to do is construct C tilde that has big enough thickness so that you can use the get value. But this wasn't working for thickness 0 sets. And now using our containment lemma, all we have to do is start with larger convex hull. And then we make smaller gaps than C. And we do that iteratively. And then C tilde is guaranteed to intersect with thickness 0 contour sets. Now we consider 2 applications. First, we're going to consider the question, when do sums of contour sets, which are totally disconnected, will contain an interval when we add them? And secondly, we're going to consider the topological version of error dissimilarity conjecture. Let's consider the first application. We define the sum of Q sets to be all possible sum of elements in those 2 sets. And by Steinhaus proving 1920 that if those 2 sets have positive Lebesgue measure, then the sum will always contain an interval. Feng and Wu proved in 2020 that if we have n number of contour sets with all positive thickness, then if we have large enough number of contour sets, it will contain an interval. However, the question remains for thickness 0 contour sets, but now using our containment lemma, we can construct another contour set C tilde, such that when we add the thickness 0 contour set with that contour set, it will contain an interval. So this is our first corollary from our lemma. We now consider to the second application. We're going to introduce the following definition. So a subset in R is called measure universal if for all positive Lebesgue measure sets, there's an affine copy of that given set. So this means that this given set is in some sense a universal pattern within all positive Lebesgue measure sets because we can put in some affine copy of it. Steinhaus again proved in 1920 that every finite set is measure universal. So we can put a finite set, any finite set, and make an affine copy of it and put it in all positive Lebesgue measure sets. So it's a universal pattern. So based on this observation, Erdős proved in 1974 that all infinite sets are not going to be measure universal. So in a sense, they're too big to be an all universal pattern within all positive Lebesgue measure sets. And there have been a lot of interesting progress behind this conjecture. For example, Bourgain proved in 1987 that if an infinite set can be expressed as a sum of 3 infinite sets, then it's guaranteed to be not measure universal. Falconer proved in 1984 that certain slowly decaying sequences are not measure universal, and Gallagher, Lie, and Weber in 2022 considered the contour sets, and if it has positive thickness, then it is too big to be a universal pattern. However, the thickness 0 for contour sets still remains open. And just wanted to note that Erdős similarity conjecture is almost reaching 50 years to remain open. So we would like to further investigate this. So people further investigate this conjecture with very different versions of this conjecture. For example, Gallagher, Lie, and Weber in 2022 considered a topological version, where they considered universality for not positive Lebesgue measure sets, but topologically large sets. So they replaced positive Lebesgue measure sets to be all dense G delta sets. And they proved that all contour sets turn out to be not topologically universal in RD. However, this was a non-constructive proof involving some arguments of Hausdorff dimension. However, they were able to construct explicit dense G delta sets that does not contain any affine copy of the given contour set if the contour set has positive thickness. Extending this work, we're able to use our containment lemma to show that for even thickness 0 contour sets, we can construct explicit dense G delta sets that will never contain an affine copy of that. So this is our second corollary. We would like to conclude this talk by a summary and a set of questions. So thickness is a very powerful notion to measure size of contour sets. And Get lemma states that if the thickness is large enough, then those two contour sets are destined to intersect. However, a natural question is, when would contour sets with 0 thickness intersect? And we can answer this question using the containment lemma that we have proved. And we apply this in 2 examples where we consider some of contour sets containing an interval and topological Erdős similarity conjecture. Now we list 3 open questions. Firstly, given a contour set C, can we construct a contour set C tilde, for example, using some variation of containment lemma, such that C tilde will have 0 measure? And this is of particular importance because it's particularly interesting because once we prove this, then we can directly prove Erdős similarity conjecture for all family of contour sets. And secondly, can we complete the generalization of the containment lemma to higher dimension? Actually, we have some partial proof that contour sets with positive Yavikuli thickness is not universal in both topological and measured theoretic sense. And here, Yavikuli thickness is a very useful generalization of Neuhaus thickness in higher dimension, because Neuhaus thickness is only defined in 1 dimension. Our containment lemma also applies to Yavikuli thickness 0 sets, but we were currently only able to generalize this to rectangular types of contour sets. So it would be very interesting if we can generalize this to arbitrary contour sets in higher dimensions. And finally, we would like to ask ourselves if we can find more applications that we can use our containment lemma to interesting problems that rely on Neuhaus thickness. And thank you very much for listening.
Any questions?
So probably I'm just not understanding what these words mean, but for the first question, can't you just pick a point in C and make that the left endpoint of the standard Cantor middle third set, which has the big measure 0 and then intersect?
Right. So that would definitely intersect. But actually, if we want to prove Erdős similarity conjecture, what we actually have to do is it has to be robust under certain amount of translation. So yeah. But, yeah. Thanks for your question.
Good. Maybe I need to read the slide more carefully, but you had this intersection for your containment lemma.
Mm.
Is it an open condition? Like, can you get an interval?
Yes.
Okay.
I want to check if I understood the question correctly.
Yes.
So here, so if this convex hull is strictly contained in the convex of C tilde, and this condition is independent of translation, so as long as the convex hull is contained, we're able to slide it around. So it's robust under a certain amount of translation.
So I might have some cool ideas for application training, but we'll talk offline.
Oh sure, yeah. Thank you so much. That's a great question.
Thickness 0, very interesting because I've only dealt with positive thickness before. There's an inequality that involves there are bounds you can give on Hausdorff dimension in terms of thickness and density. And this bound involves a 1 over thickness. So I was wondering, are you able to give any bounds, any idea of what kinds of Hausdorff dimension is possible in a thickness 0 Cantor set?
Right. So I think that's also a very interesting question. So we know, yeah, as you just mentioned, well, to answer the question, I don't know. But yeah, we know that there's a lower bound given by the thickness on the Hausdorff dimension. And as far as I know, that assumes the thickness to be positive.
Right.
So I think, yeah, it will be an interesting question to pursue in the future. Yes.
Can I ask a question about the definition of Newhouse thickness here? Now, at the beginning, you defined Cantor sets to be these, perfect sets, totally disconnected, right? But maybe I missed the slide. Okay. Newhouse thickness, it seemed you defined only for Cantor sets you generate by removing gaps.
Right.
Yeah. Do you have is it only for those type of Cantor sets?
Right. That's also a very important question. But for all contour sets in R on a real line, so we can always
all of them can be constructed.
Yes.
Oh, I didn't know that. Okay, interesting. Okay, all totally disconnected perfect sets can be
I think
constructed in that way.
Yeah, we can take the complement, and that's gonna be open. And there's only countable many.
Okay.
We can order them and then remove those gaps.
Oh, good. Really cool.
Any further questions? Last thing?